this process, occurring naturally in the cosmos, has been replicated on Earth in high-energy environments such as hydrogen bombs and experimental reactors like tokamaks and stellarators. However, these methods require extreme conditions, plasma heated to hundreds of millions of degrees and confined within powerful magnetic fields. The engineering challenges are monumental, to say the least, and despite some promising advances, controlled fusion remains just beyond our grasp. Now, cold fusion, in contrast, proposes an alternative: the ability to induce nuclear fusion reactions at or near room temperature without the need for vast energy input or those extreme containment methods. If realized, this would revolutionize our understanding of nuclear physics and energy production. It would mean the ability to generate vast amounts of power without the hazardous radiation and toxic byproducts associated with fission, and without the need for the sprawling infrastructure that conventional fusion demands. It would mean decentralized energy production, where even a small device could power homes, cities, or even spacecraft with minimal fuel. It would mean the end of energy scarcity, with the potential to lift nations out of poverty, free industries from the burden of fuel dependence, and mitigate the devastating effects of climate change. But why has this dream remained so elusive? What scientific principles make cold fusion so difficult to achieve? And why does it continue to generate both hope and skepticism? Well, at its core, fusion requires overcoming the Coulomb barrier, the electrostatic repulsion between positively charged atomic nuclei. In high-energy fusion, as seen in stars or those experimental reactors I spoke of, this barrier is surmounted through sheer thermal energy, allowing nuclei to collide with enough force to trigger fusion. In cold fusion, however, a fundamentally different mechanism must be at play, one that allows nuclei to merge under conditions where classical physics tells us that they should not. One of the most famous cold fusion experiments was conducted in 1989 by Martin Fleischmann and Stanley Pons, who claimed to have observed anomalous heat production in palladium electrodes loaded with deuterium, an isotope of hydrogen, during electrolysis. This announcement ignited global excitement, but replication attempts yielded inconsistent results, leading to widespread skepticism. Critics pointed to the lack of clear nuclear signatures, such as neutron emissions or gamma rays, which are expected byproducts of fusion reactions. The absence of these hallmarks raised fundamental questions about whether true fusion was occurring, or if some unknown, poorly understood phenomenon was at play. However, despite initial setbacks, cold fusion research has persisted in various forms. Some scientists propose that quantum mechanical effects, such as tunneling or lattice confinement within metal hydrides, might facilitate fusion types of hydrogen, deuterium and tritium, both of which can be extracted from seawater or synthesized with relative ease. This means an effectively limitless fuel supply. Moreover, fusion reactions produce helium as a byproduct rather than radioactive waste, making them far cleaner than fission. And unlike wind or solar, which depend on environmental conditions, a working cold fusion reactor would provide continuous power free from the unpredictability of weather patterns or daylight cycles. Consider what this could mean for transportation. Electric vehicles, already gaining traction as a cleaner alternative to gasoline-powered cars, are currently limited by battery technology, charging times, and grid dependence. A compact cold fusion power source could eliminate these constraints, allowing vehicles to travel for months or maybe even years without refueling. The aviation industry, a significant contributor to carbon emissions, could be revolutionized by aircraft powered by small fusion reactors, reducing fuel consumption and emissions to almost zero. Beyond Earth, cold fusion could fundamentally change space exploration. Current spacecraft rely on chemical rockets or nuclear fission for propulsion, both of which have severe limitations. A cold fusion engine with its immense energy output and minimal fuel requirements could enable long-duration space missions, opening the door to Mars colonization, asteroid mining, and even interstellar travel. But this isn't just about convenience or economic gain. Cold fusion represents something more fundamental: the possibility of breaking free from the constraints that have long defined our technological progress. The energy equation has always been one of scarcity, trade-offs, and compromise. But what if, for the first time in history, we could achieve abundance? What if we could power the world without conflict, pollution, or fear of depletion? This is why the search for cold fusion continues despite decades of skepticism. The potential reward is just too great to ignore. The question now is whether we're on the brink of a discovery that will redefine civilization, or if we're still searching for a phenomenon that remains well beyond our reach. So as we look forward, we need to ask ourselves, are we approaching the moment where cold fusion transitions from speculative science to tangible reality? What challenges still need to be overcome? And how can we separate the signal from the noise in this field? First, we need to acknowledge that persistent skepticism surrounding cold fusion. The scientific method demands reproducibility, and historically, many cold fusion experiments have failed to yield consistent, verifiable results. However, this doesn't mean we should abandon the search. Great scientific breakthroughs have often been met with skepticism in their early stages. Consider the resistance to the germ theory of disease, the initial dismissal of quantum mechanics, or even the skepticism surrounding nuclear fission before the first chain reaction was successfully achieved. The key difference between pseudoscience and illegitimate advanced matter physics, particularly the study of how hydrogen isotopes behave within metallic lattices. Palladium, for instance, has a unique ability to absorb large amounts of deuterium, leading to extremely high atomic densities, potentially high enough to encourage nuclear interactions under the right conditions. Some researchers speculate that within these confined environments, quantum tunneling could allow deuterons to overcome the Coulomb barrier at much lower temperatures than classical physics predicts. Another hypothesis suggests that electron screening effects within metal lattices could alter the fundamental nature of nuclear interactions, creating pathways for fusion that don't produce the expected neutron emissions or gamma radiation. If true, this would challenge our current nuclear models, necessitating a deeper examination of the forces governing atomic behavior at low energies. This alone would be a monumental shift in physics, even before considering its technological applications. Recent advances in material science and nanotechnology may offer new tools for investigating these phenomena. Highly ordered nanostructures, precision engineered lattice defects, and advanced catalysts could help optimize the conditions under which cold fusion might occur. Cutting-edge spectroscopy and particle detection methods are also improving our ability to identify and analyze anomalous heat production and nuclear byproducts, allowing for more rigorous testing of cold fusion claims. Moreover, the emergence of artificial intelligence and machine learning offers new ways to analyze vast data sets, identifying subtle patterns that human researchers might overlook. By applying AI-driven simulations and data modeling to cold fusion experiments, we may uncover hidden variables or optimal conditions that have eluded researchers for decades. But what would it take to make cold fusion not just a theoretical breakthrough, but a practical energy source? First and foremost, any working cold fusion system needs to be both scalable and controllable. It's not enough to produce excess heat in a laboratory setting. We need a reaction that can be reliably initiated, maintained, and regulated, much like conventional nuclear fission reactors. Without control mechanisms, even a successful cold fusion system would be impractical for widespread use. Second, the reaction must produce a net energy gain. Many experiments have claimed to observe excess heat, but the energy input often still exceeds the output. To be viable, a cold fusion device must provide a clear and significant energy surplus, one that can be efficiently harvested and converted into electricity or mechanical work. Third, reproducibility is key. Any claim that cold fusion has been achieved must be independently verified by multiple research teams using standardized methodologies. Without this, skepticism will continue to dominate the discourse, and mainstream scientific funding will remain limited. The implications of success can't be overstated. If a functioning cold fusion reactor were developed tomorrow, it would rapidly alter global energy economics resource distribution. Every nation, regardless of its natural reserves, could generate its own power from a nearly inexhaustible supply. The economic and geopolitical shifts would be seismic. Environmental impacts would be equally profound. The transition from combustion-based energy to clean fusion-based power would drastically cut greenhouse gas emissions, offering one of the most effective tools yet in the fight against climate change. Entire regions of the world currently plagued by energy poverty could leapfrog directly into a post-carbon future, just as some developing nations bypassed landlines and adopted mobile phones directly. And beyond Earth, cold fusion could absolutely revolutionize space exploration. Current space missions are bound by fuel limitations and energy constraints, making long-duration travel extraordinarily difficult. A compact, portable cold fusion power source could enable deep space missions, power future lunar or maybe even Martian colonies, and maybe even open the door to propulsion systems capable of interstellar travel. The road ahead is challenging. Science is not built on wishful thinking, but on rigorous experiments.